everyone, thanks for joining another educational video on the TechniSci channel. In this video, we're looking at graphs. We're going to look at scaling them, plotting them, as well as finding the gradient. So come plot with me as we explore this concept. Okay, so to go through this concept, we're going to be looking at a portion of the CSEC Physics 2021 paper. We're looking at question 1. So the question reads, to determine the spring constant or stiffness of a spring, a student placed masses, symbol for masses M, on a hanger that was attached to a spring and recorded the length L of the spring. Table 1 shows the mass and corresponding values of length. So even before we get into this question, I'm going to be showing you a demonstration of what this experiment would look like. So to highlight the concept that is being brought out in this question, I am going to be using a Phet simulation called Masses and Springs. I'll link it in the description below to show what happens. So you will have the spring, and this is the length of the spring before anything is added to it. So this is what we refer to as its natural length. No weight is added to it. It has a length of 45, 46, 47, 48 centimeters. So that's the length when nothing is on it. Now I'm going to be putting a 50-gram mass on the spring, and then now you're going to see what happens. So let me just stop that. So once we do that, you see that the spring now has a new length. So it now is resting at 55. It's now resting at 55 centimeters. And this green arrow here is demonstrating the extension that the spring has gone through. So the extension is basically the change in the length as you add a certain mass to the spring. So I'm going to add more. So I'm bringing it up to about 100 thereabout. See if I can get it to 100. All right, I got it to 101, 104. All right, getting it to 100. It's a little bit on the difficult side, but you're seeing the difference. Let me stop it again. So you're seeing the correspondence. As I increase the mass, the length also increases. So now at 102 grams, it is now at 63 centimeters. And this will be the case as we go. We add masses to it, and when we check the extension, we will see that it has increased. So now let's get back to the question that we were working on. Okay, so welcome back. Now let's look at the table that we were given. We are seeing mass in this column, force in this one, length here, and extension. And you'd recognize that under force and extension, there are some rows that are blank. So let's explore what question we were given for this table. It says, complete table 1 by inserting the missing values in columns 2 and 4 respectively. Beautiful. So that's what we're required to do. Okay, so for column 2, we need to put in force. Now we have mass. So that means we can apply our formula. Force is equal to mass times gravity. Now gravity is equal to, putting it down here, 10 newtons per kilogram, and can also be used as 9.8. However, given this question, we're going to take the relation. Looking at the first row, we're seeing that the mass is 0, meaning there's nothing on it, no mass is added. And so like if there's no mass added, then there's no force. So force is 0 as well. Now the length, 70.2, that is telling us that the length of the spring when nothing is on it, the original length of the spring is 70.2 centimeters. So that means there is no extension. No mass added, no extension. So then we look at the second row, and we're seeing where the mass is 0.1 and the force is 1.0. So remember I said there are two values that we can use. We can use 9.8 newtons per kilogram, or we round it up to 10. So given the relation between these two values, we can see that the value used in this question was 10, and so we'll be using that value. So if I will just calculate the first one, is equal to 0.2, and this is kilograms, times 10 newtons per kilogram, trying to get it all to fit right there. So then we will have 2.0 newtons. So that means this column, this row, will be 2 newtons. So I will just continue and calculate the others. Okay, so there are the values for force. Now let's look at extension. Okay, so let's look at extension. Remember, the original length of the spring is 70.2. When the mass of 0.1 kilograms was added, it went to 74.4. Based on the first row again, we can see that the extension was 4.2. Let's see. Extension is equal to, and I'm just going to use letters to represent it, new length minus original length. Okay, so the new length is 74.4, and I would usually put centimeters, but my spacing is not adequate for that, and 70.2 there. So 74.4 minus 70.2, we get 4.2 centimeters, which is what is there. And so we will just continue and complete the table. Okay, great. So our table is now complete. We can continue. Let's go to the second question. Plot a graph of extension. Symbol for extension is E versus force. Symbol for that is F. Now remember from my first video on graphing, I mentioned this statement. Let me just underline. I mentioned that statement. You will always get that instruction. Plot something against something else, or something versus something else. So in this case, extension is being plotted against or versus force. What does that mean? Extension goes on our y-axis, whereas force goes on our x. So remember, first quantity on y, second quantity on x. And how do we know first quantity? Whichever one goes before the word versus or against. That's how we know. So let's now go over to our software that we use for plotting graphs and get to this one. So I'm using Microsoft Whiteboard to help me with this graph. And I've moved the question over to here, asking us to plot a graph of extension versus force. So now we are getting into doing our graph. So now we have to consider what scale are we going to use so that we're able to find the values. And I'm going to highlight the values. Okay, so now we want to see what scale we're going to put on the graph to be able to plot these values. Remember, you should not try, especially for the values on the y-axis, you should not label your axis with these values. Think of it as you putting a ruler on the screen, like you see here. You have, this is a 30 centimeter ruler. If you wanted to measure up to 22.5, you couldn't use 15 centimeter ruler. So that basically means that whatever scale you use, you should be able to get this value here, 22.5. So you can't make the scale so short that you cannot get up to 22.5. Have to make sure that you get it. You also have to make sure that the graph covers more than 50% of the paper in the vertical direction as well as in the horizontal direction. So that's another consideration. So just like this ruler where you're seeing it increasing, 0, 1, 2, 3, you recognize that every value is an increase of 1. So the first value after 0 is 1, 1 plus 1 is 2, 2 plus 1, 3, 3 plus 1, 4, and so on and so forth. And remember, you should check the axis first to make sure, so that based on where you are planning to put the y-axis, you will get the values that are for the x. So now I see that the values to be plotted are 0, 1, 2, 3, 4.25. So if I decide to put my axis here, on that vertical line, my y-axis. Let's check. Let's check a scale of 2 centimeters. So that's 2 to 1. I'm going to use 1, 2, 3, 4, 5. So my x-axis values to be plotted would end there. So that was suitable because it would be more than half of the x-axis. Based on the grid, we wouldn't be able to do it any smaller than that. So we're going to work with that. So that means our y-axis is suitable for this line. Okay, so now for the values for the y-axis, that's the extension values. So we have 0, 4.2, 9, 13.7, 18, 22.5. Let's try a scale. Let's try starting the x here. So you know that line would be your 0. So let's try 2 centimeters to 2. So I'll go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so this would be 22. So that would not work. But let's see if I could drop the x-axis here and see if that would work. So go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So that means this would have been 23. So we would be able to get 22.5. So that's perfect. Okay, great. So putting the x-axis on this line will work for us. Let's do that. And that's how you determine your scale. Remember, it can't just be that you look at what is to be plotted and write those on your axis. Because example for the x, you have 4.2. You couldn't label 3 then 4.2. That would not be a proper scale. Each value must increase by the same amount. Likewise for the y, you can't just put 4.2, 9, 30. No, because that way you will not be able to have a proper scale to be able to read any values from. So you have to use a regular scale, one that increases by the same amount for each mark for your scale. Okay, so now we need to find the points to plot. So I'm going to write on the scale. Remember to label your axis with the symbol for the quantity / the unit, or you could have written out the words, but you must put your quantity and unit for each axis. Now, because we're increasing by 2 for every 2 centimeter, it simply means that for here, it would be increasing by 1. So this would be 21, this would be 22. So that means this is 23. So we would be able to find 22.5. Just establishing that again. An extension symbol is E/cm. And we put that. This is the y-axis here. And we put our x-axis here. Okay, so now we are ready to find our points to plot. So when we are doing this method, we are going to be using our lines as guide. So our first point to be plotted is 0 for force and 0 for extension. And you must plot those. You can't ignore it. You must plot 0, 0. That's our first point. So I'm going to zoom in. That's our first point, 0, 0. 0 for x, 0 for y. And the origin is where you find 0 for x, 0 for y. Next point, 1 on force, 4.2 for extension. So force is on the x, I find 1 here, good. And then I'm going to need to find where 4.2 is. So here is a little formula that works. To find the value of the divisions, the smaller divisions, we use this formula. So smaller divisions, sometimes I call them subdivisions as well. Okay, so this formula for the smaller divisions, it's the scale increment divided by the number of spaces between. Let me finish that off. All right, so it's the smaller divisions equal to the scale increment divided by the number of spaces between increments. So that would be, we have 2 here, that's our scale increment, it's increasing by 2. That's what increment means, how much it's increasing by. So each time we have here, it's increasing by 2. 0 plus 2, 2, 2 plus 2, 4, 4 plus 2, 6, 6 plus 2, you get the gist, good. So my scale increment then is 2. And the number of spaces, I can zoom in to show you that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10. And we know that 2 divided by 10 gives us 0.2. So for the y-axis, each of these smaller lines increases by 0.2. Now I like to do a check just to make sure that I would get the correct answer. So 0 is here, 0.2 plus 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, 1.8, 2.0. So then based on our check, we recognize that that scale value, that scale increase is correct. So on our y-axis, we are increasing by 0.2 for the smaller divisions. Now, can you do a quick check and tell me what this scale increment is for the x-axis? Got it? Okay, let's work it out. So the smaller divisions, and I'm going to be calling it ST this time around, will be equal in this case 1 because it increases by 1 each time, divided by, and once, another trick, once it's 2 centimeters, there will be 10 spaces. So I already know that. 1 divided by 10 gives us 0.1. Now for the check, 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0. So that means that our values for the smaller divisions is correct. So we can continue. We were looking for 4.2 on the y-axis. So let's go. We find 1. So now 4.2 would be at this position. And you use the same plot type to plot each point that you are plotting. So make sure you're sticking with the plot point. We're going to do another one together and then we will finish up. So the next one, 2.0 on the x, 9.0 on the y. That one is easy to find. 2.08, 9 would be right here. Remember, each 2 centimeters we're increasing by 2, but halfway between 10 and 8 would be 9. And so that's how we know that's where that is. One more, and then you finish up. 13.7. So this is 3 newtons with 13.7. So this one might be a little trickier to find because it won't necessarily be on a line. It will be in a space. And so when that's the case, we try to get it as close as possible to what it should be. So this is 3, this is 13. So let's go now, 13.2, 13.4, 13.6. So 13.7 would be right in the middle here. Good, so you make sure you put it right in the center of the space. Now continue. Okay, great. So now we have plotted our points, all points. We have 1, 2, 3, 4, 5, 6 points, and that corresponds with the 6 that were given in the table. So we have plotted our points. Now we're going to finish off our graph. So I'm going to get my ruler again. Now we're going to be drawing a line of best fit. Now for this procedure, you take your ruler and you try to line it up that it passes through as many points as possible. For all the points that it does not pass through, you try to balance that on both sides of the line. Alright, so after drawing my graph, setting my ruler, this is the best way I'm getting it. Now, please note that for this graph, whereas it falls through the origin, for this graph, you don't have to always try to get your graphs to pass through the origin. Sometimes it will align with the origin properly, sometimes it won't. But guess what? Do not be beating on yourself about trying to get it to pass through the origin. Okay, so now that we've done this, we're gonna now be finishing off our graph. We're not yet done. For us to have a graph considered complete, we must have a title for the graph. Must have a title for the graph. And if you're doing labs, it goes just the same. Not just for your exams, but whenever you plot a graph, you must have a title. Let's assess. So we talked about which quantity goes on which axis. So you know, first goes on y, second on x. We spoke of how to scale it, make sure that each number increase at regular intervals. And we spoke of how to plot our graphs, how to draw our line of best fit. And remember, it's called a line of best fit because it is basically the average of the points. So it is not going through all the points. And please do not connect the dots. It's not going through all the points, but it is positioned so that it is the best average of the points plotted. Good. So now we're going to title our graph. Now our title is usually placed at the top of our graph paper in the middle, but because our graph is all the way at the top, it ends at the top. We're going to be putting the title a little bit to the left, and then our scale should be at the top right. So we're going to put in the scale on that side as well. And we write our titles in full caps. Okay, so there we have it now. Our graph is properly titled. We have our scale written. Please make sure that when you put your titles, everything for the graph fits within the grid. Do not write in the white portion of your graph paper because anything can happen and that portion becomes damaged and then the data you have there becomes lost. So try to keep all that you write within the grid section of the paper. Now, what do you notice about the title? It's similar to what you were told to plot. So all you put graph showing extension versus force. I use the short for versus, which is VS, and it told you to plot extension versus force. So you know exactly what your title is based on the instructions you were given. My scale for the x-axis, every 2 centimeters represents 1 Newton. For my y-axis, every 2 centimeters likewise represents 2 centimeters. So we are fine with that. And we can now go on to there was another question that we are to do to calculate the gradient of this graph. Let's get to it. So here's a question, calculate the gradient of the graph. And they gave you a specific letter. Another tip, whenever you're plotting graphs and they give you a specific letter for the gradient, we know we usually use M for gradient. Make sure you use the letter that is given. It usually is related to the question that follows. So make sure they say gradient, comma S. They're telling you that the symbol for gradient in this case is S. So always use that. So now we're going to be doing a gradient. To get our gradient, we first have to find 2 points along the graph that is not plotted. We do not use plotted points to find gradient. So let me show you how we're going to do this. You're going to look along your graph, and I usually tell students to use points between the first and second plotted points. So that would be this one and this one. We use those, and then between the second to last and the last. Why? Your gradient points are to spread for the majority of your graph. They're to spread for the majority. So your gradient is to take up more than 50% of the graph. And remember now, the graph is the line we draw. It should be taking up more than 50% of that. So let's zoom in now and see if we can find a point. Now, again, another tip I usually give my students, find a point along the graph that runs through the intersection of 2 of the grids on the paper, like here. What that does, it makes it easy for you to read off the coordinates here. Just like in math where you have coordinates, it's the same thing. So once your graph is passing through a point like this, where it intersects the X and the Y grids, then it's easy to find the value. So I'm going to choose here. Now, because I used an X when I was plotting my points, when I'm doing gradient, I'm going to use dot and circle. Dot and a circle around that. So that's point number 1. And I'm just going to read the values immediately. Point number 1, just like with math, we have coordinates X, then Y. So my X value will be what? Remember, this increases by 0.1. So 0.1, 0.2, let me count up here. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So this is 0.6. And the Y increases by 0.2, each small division, 0.2. So this is 2.0, 2.2. Let's go over here. So 2.0, 2.2, 2.4, 2.6. And these would be X1, Y1. And the reason they are 1, the point that falls closer to your y-axis, closer to your origin, that is your point 1. We call it point 1. Not 0.1, no. P-O-I-N-T, it's the first point. Let's say that. First point. Now let's find our second point. Second point is the one further from the y-axis at all times. So let's now look. Oh, wow, found one here. Beautiful. So again, dot and circle. That way I make a clear distinction and individuals marking my graph can know, okay, these are the points I used for my gradient. So now let's try to read the points here. Let's see what this bright line represented. This is the one. So it represents 4. So I can add going across now. So this line is 4. And remember the x-axis increases by 0.1. So 4, 4.1, 4.2, 4.3. Will it hold? No, I'm going to put it And then now let's determine y. This is the bright line. This would represent 19. So let's come here. And remember, it increases by 0.2. So 19, 19.2, 19.4. That's my y. And this will give you x2, because it's my second point, y2. And you're going to see why we need to indicate x2, y2. Now the gradient formula is S is equal to, and remember it would be M or whatever letter they tell you to use for the gradient. So S would be equal to y2 minus y1 divided by x2 minus x1. Now please note the 2's and the 1's are subscripts. They are not squares, so do not write them as a square. They are subscripts. They are just used to identify the first point and the second point. So they are subscripts. This formula, another formula for gradient, another way of representing gradient, we say the gradient is equal to rise over run. So we say vertical rise over run. So we know that rise, the y-axis rises, the x-axis is running. You know, if you're running horizontally, right? So it's rise over run. And then that now can be broken down into this equation. y2 minus y1 divided by x2 minus x1. And now we're going to be substituting our values. So let's go for my y value, y2. My y2 was 19.4. Let's find y1. y1, wait, I'm going to put the unit. I find it's better when students are to determine the unit. So let me put the unit. 19.4 centimeters minus 2.6 centimeters divided by x2. What was that? 4.3? Yes. 4.3 newtons minus, let's go for x1, 0.6 newtons. How we know it's newtons? Because the unit on the x is newtons. So now let's do our calculation. Okay, so now let's get the final answer. And simple rule of calculations, when we are writing answers, we write them to the smallest significant figure of the smallest one in the calculation. So the smallest figure is 2. So our answer should be 2. So it's 4.5 centimeters per newton. And that is for multiplication or division. You maintain the smallest significant figure when you are multiplying or dividing. Another way persons would write this would be 4.5 centimeter, showing that this is a denominator. Works just the same. So we have gone now and completed our graph. We completed our table, we plotted our graph, and we calculated the gradient of the graph. That now puts a wrap on the activities for this video. Just before I wrap this video, I wanted to show you how to get your triangle to represent your gradient points. So you're going to take your ruler, put it along the point 2, and you will draw a vertical line. And then from point 1, put in a horizontal line. And that's now how we will help to determine that the points used for the gradient produced a large triangle. You're seeing horizontal and vertical sides of the triangle and your graph line representing the hypotenuse. So I hope this video was helpful. I hope you now are better able to plot your graphs and to determine the gradient of your graphs. Thanks for joining. Remember to give the video likes. Remember to share it with your friends so that they too can benefit. And if you have not subscribed to the channel, subscribe. All right, everybody. Thanks and see you in the next one.